All right, let's get going, huh? All right, so this talk is about HBase sizing nodes. It's sort of like wraps up the experience I've gathered over like running HBase clusters for a couple of years. There's a few sort of, I'm trying to boil this down to a couple of easy to remember rules. I have some cheat sheets at the end, so you can actually use those, hopefully. And if you ever use HBase to somehow help you come to terms with it. Just for like to get started, who actually uses HBase? Okay, quite a few. Who thinks about using HBase? Okay, all right, always a choice, right? Good. A little bit about me. I work for Cloudera. Wear my shirt today. I'm like in the other conference up north, so that's why I'm officially here with the shirt. I'm the chief architect for Europe, like EMEA, anything outside of the US, but I'm here quite often as well. I am a committer at HBase and at Weir as well. Only mostly like the recent months or whatever the recent year. I can't do that much. I mean, if you look at the charts, I'm the one with the fewest commits, but I'm trying to stay current at least. And I'm also the author of the O'Reilly book for HBase, the definitive guide. Have to actually update it, so there should be a new one coming soon as well. And there's my contact in case you have any questions. So let's sort of frame the picture of what I'm going to talk about. I said earlier, I'm giving you some cheat sheets at the end. The way I see this, basically, if you were to talk about sizing a HBase cluster, you could talk about how many machines do I need. You just throw like, I don't know, machines together based on the total size of data that you want to store, or you have already machines which has, I don't know, a certain amount of terabytes per machine. These days, if you go for commodity hardware, that's somewhere they say 6 drives, sometimes 12 drives, 1 or 2 terabytes of disk, then divide this by 3 to get the size that you have effectively usable through HDFS. That could be sort of like a ballpark figure of saying, okay, I need to store, I don't know, that much data, so I need 10 machines, and off you go. That's just like a very easy one. But obviously, you somehow also want to make sure that you actually saturate the cluster most efficiently. Because I've seen it that if you do that sort of back of a napkin calculation, and you run your data or you run your workload, you still might suffer, or the cluster seems like it's hardly doing anything. So it's a good idea to somehow understand how the sort of a few things work underneath the hood to do a better calculation on how many machines you need. So I'm sort of trying to. So if you really want to do the cluster sizing right, you need to understand a bit of that low-level stuff. I'm not going too deeply. I'm just explaining a few things, a few moving bits and pieces, which are important that drive the performance of HBase. And that helps you hopefully then to really understand what you have to do for your use case. So HBase sizing is a couple of things. As I said, understanding the hardware or the software, understanding hardware and studying the software, mix this with your use case, and then somehow figuring out how many servers you need. So let's look at what's going on really sort of on the first level underneath the hood is I'm calling the sort of competing resources. We have the problem that reads and writes essentially, although I have to say at the bottom there, although they really exercise completely separate code paths in HBase. The way it's designed is really fairly separate everything. They still have on the lowest level competing resources, which is the shared stuff. Like it shares underneath the hood HDFS to write the data out, like the file system. It shares the network. You have to somehow get data in, get data out. So whenever you run out of sort of the shared resources, you shit out of luck anyways, basically. So you have to figure out, for starters, what are my shared resources, how much load can I put there. So you have to come to terms on that level as well. Then there's something you can actually configure. For example, there are RPC handlers, like those remote procedure call handlers that's used between HDFS and HBase, between your client and HBase, between your client and HDFS. So all of these have thread pools that can be configured. And I've seen it actually in reality that someone just had it set by default. I had left the default and would put load onto the cluster, and then we came to realize that something is going really slow or something eventually hit the roof. And very easily, you just increase that number, for example, because you can look at this using metrics, and then you can get past that point and move on. So you can get more out of your cluster. So sizing is finding these knobs and turning them into the right direction. So handlers and threads is one of them. And the other thing is, and that's what I'm going to talk about a bit more in this presentation, is what happens with memory. How much memory do I have per machine, and how does it actually drive what I can do with HBase? So memory is the important one. Talking about memory sharing, like if you talk about the memory itself, if we go back to that, the sort of the core part that you do in HBase is you have to divide memory between those reads and writes that I mentioned earlier. Though there are separate entities, like there are separate code paths, they're handled very separately internally, you still need to decide how much memory you set aside on either side. So by default, there's a rule where it says divide this into roughly 3 areas. One is for writing, which is the in-memory stores. So there's a way that the system stores data in memory. We get to this in a second. That needs some memory. Then there's another part, the second part, which is for the actual reading. That's called a block cache. Typically, it's a cache. You're loading blocks, and you're keeping them in memory so that they stay warm for subsequent reads. That's the reading side, and then there's the rest of it. So if you put this together, you have 60% only being assigned to these two, like reading and writing, and the remainder goes towards everything else that is going on in the system. So these three parts which you have to look at, and you should tweak them based on your use case, right? So depending on if you do a lot of reading, then you want to tweak it towards the block cache. If you do a lot of writing, you might want to tweak a little bit more towards the writing part, like the in-memory stores, and give it more memory. Overall, I've seen in practice a lot of people, when you put together like 60% and 40% for the rest, they take away from the rest very early on. They say, oh, well, 20% is enough for the rest. So we have another 20% of the heap that we give to the Java process for other stuff, say for reads or for writes. So this is very common that you start cutting into those depending on your workloads, but you need to tune those. So let's look at these two paths, the reading and the writing, separately, so that we can address both separately and talk about it, how to tune those and size the cluster properly. During reads, the way this works is that the client has to first find where is my data, and that happens in HBase through like the zookeeper. We don't have to do this. The client does that. The client goes out and asks who has the data, where's my table that indexes where my data resides. It looks this up, it goes through a root and then meta table. But I mean, in newer versions we actually drop the root table. It goes only through one hop, but there's a hop that it has to do to first find where data resides. That's the first thing where you can actually look at to improve your performance as well. There's a tunable parameter that you can actually specify to increase the prefetching, for example. So if you ever have to go out and say, okay, where's row 15? Okay, that's on server 3, so that you remember this for next time, that's fine. But now you're looking for row 1 million, and then it tells you, well, that's on server 20 or something. And then you keep like sort of asking for stuff, and eventually you have a picture of where data resides. But this takes a while. And so during ramp up, you will have a few more hops before you finally have sort of the picture of what you need for your working set to do the work from the client side. So the client caches this. If you want to have a little bit faster startup, if you're ever concerned about HBase taking a bit of time to warm up, you can actually tune this to say, I increase the prefetch option, set this higher to fetch more in one go. So whenever you look up the first one, you could get like a couple of them in one go, and then you already have that information, so that you don't have to look up anymore. So that's one of those that is just a nice way of sort of tune the startup versus the warm-up basically versus the startup latency. Then once it has found the server, so now knows where the data resides, it has to go to that server, and now the server has to say, okay, what do I need to access? Which files do I have to read to reconstitute the row that you're asking for? So if you're asking for a certain row in HBase with a certain amount of columns, it has to go out and say which of the storage files underneath have that data. And that's where you can also again tune and make your cluster more efficient by looking at if you can use ranges, like time ranges, for example. So they can say, I'm looking for data that's only like a day old. So if the data is a day old and you know that you only need data that has been changed the last day, you should hint this to HBase through the client when you do the get or the scan operation, because then the lower level system can say, I have like 10 files here, and only the last one is within 1 day. All the other ones are older than 1 day, so therefore skip those files and don't even touch them. If you don't do that, it would just go out and would touch all of these files, which goes towards your shared resources. It would go through HDFS, read blocks, and you take away shared resources that you could use better and more efficiently on other places. So look at time ranges. If you can hint what you want to have, then specify that. And there's also a feature in HBase called Bloom filters, which are interesting. If you have the right use case, then you can use Bloom filters as well to eliminate the files that have to be touched. There are, sort of like just as a rough idea, if you do random updates, then Bloom filters are probably not good for you to use, because if you do random updates on existing rows, then you will have changes to that row in pretty much every store file. And so every store file, the Bloom filter will tell you, yes, something is in here, yes, something is in here, and so on and so forth. So that it doesn't help much. But whenever you say you do time series data or like any ledger data where you write into HBase and you're only reading it later, so you never touch that row again, then the Bloom filter is very efficient for those. So have a look at which ones are useful, which aren't. Now, it identifies what block it needs. So that they said, okay, there's a file, I need this block out of that file. Block sizes here is not like the same as a block file in a file system. We typically have in HBase, in its raw store files, 64 kilobyte block sizes, which you can also tune for your workload, but by default it's 64 kilobyte. It will, once it read one of those blocks, it will go into this block cache, which I showed you earlier, which has 20% of the heap. So it will try that first, always. It will always say, give me that block out of the cache. And if the cache says, sorry, don't have it, then only then it actually hits the disk. So optimizing all the way to this point helps you taking load away from the shared resources and do it more efficiently.
If you do a lot of random reads, do you have a recommendation for setting the block size?
So you should look at your metrics. There's a metric for the block cache hit ratio. If that is pretty bad because you're doing like really just complete random lookups. One of the examples I had in the past was, say you implement like a cache and you don't know what the user is asking for, so you don't know what's cached, what isn't cached, and so HBase is like a large cache for you. Then you really don't have much of a hit rate on the block cache because you're going left and right, left and right. In this case, you pretty much always look up the data on disk anyways. Then, if you don't do any writes, just leave it as standard or ramp it up as far as you can to get a little bit better hit rate. But if you're also doing lots of writes on the other side, then rather give more memory to the right side, because the cache is mostly a miss anyways, right? So typically the setting is based on this sort of ratio. It's quite random gets. This is why it only gets 20% of the memory and 40% for the writes. If I were to do only reads and do bulk loading, for example, from the side, so I don't even use the write path at all, I would give most of it to the block cache, although I still have probably not a good, an ideal hit rate. So you can tune it that way, depending on your write part as well. So you have to sort of balance these out. Yep.
Will the block cache correspond exactly to the segment on the disk?
Yes. Yes. So there's so they're called H file underneath HBase files, H file. And they have 64 kilobyte blocks which are indexed through a trailer, which are always kept in memory. So whenever you ask for a specific row, the block is being loaded from disk, and that 64 kilobyte is just put straight into the cache as it is, basically like raw information, so that next time you would ask for something that is in the same range, you would get it out of the cache. And maybe tuning the block size can also help you. If you do have a bad hit rate, but you still what is random, right? So if your random reads are not completely random, but more like localized, you could think about maybe increasing the block size in the H file to get slightly larger blocks which have a slightly better hit rate, right? So because you're loading the larger ranges, so next time if it's not completely random but more like regional random, then you could tune it that way as well. But yeah, it's just a block basically as it comes out of disk. And that block is really just key values, like they're just the values that actually represent the rows and the columns in the row. It's fairly straightforward. Right, so that's basically the read part. So again, that helps you sort of come to terms with the moving parts there. Now, just a bit more on the block cache. So good that we already touched upon this just then. There is a metric, so look at those metrics. If you use Ganglia, for example, as a front end for the metrics, you can just basically, the newer Ganglia interfaces, which are quite nice, you can just sort of like type ahead and just type in block cache, and you can get all of the metrics that match that block cache. So any metric that starts with or has block cache in its name is interesting just to look at while the load that you typically experience is running. Have a look at those caches and see the rate. There's another one that we didn't just touch. So one is the hit rate, like the hit ratio. The other one that is interesting is there's an eviction rate. The eviction rate gives you an indication of how much churn you have and how much memory you have, and then filling that memory, which means if you have a certain amount of, say you have like 2 gigabytes of memory set aside for the block cache, and the eviction rate stays low, it still means that you're not pushing out older stuff too often. You still have a sort of your working set still sort of fits in there quite okay. You might still have misses, but the ratio between misses and actually throwing them out for completely new blocks is not too bad. The eviction rate, if that is high, it just shows you that you do completely random. There's no way that you actually can optimize it further, because the eviction rate would say, every time I load a block, I have to throw another one out because I'm full and that's all I can do. So at peak, you would have both up if you are completely random. So this is exactly that point. Random reads are not ideal for the block cache, but you can't do much about it. Yeah, tweak those up and down. There's actually a setting inside the block cache. You can also specify how often it evicts. So if you are really into like the low-level optimization of HBase, there's a couple of settings in the block cache that you find in the configuration where you can actually specify how quickly it throws things out. So sometimes it makes sense to sort of tune this a bit more. There's a few settings that you can sort of optimize on that level, but yeah, in the end it's just memory. Throw more memory at it. The thing is, you can't switch it off. Even if you set the overall percentage down because you have like a bad rate anyways, and you don't need the memory, then you can't really just turn it completely off. Because if you were to do that, also system tables and other things wouldn't have that cache, and it goes really slow, the whole system. So if you turn it off, it's pretty bad. Set it low, but leave it at a low level, but don't turn it off. On the right side, getting on to the other side, this is really what the cluster size drives, at least the way I see it, because getting data into the cluster is the primary reason for the cluster to serve data, right? If you can't quickly enough absorb data and write it into the cluster, then the entire cluster, probably for the reading side, is not really helpful because you're missing the data, which has to be in there in the first place. So typically what I see is that for the sizing a cluster, the right performance is the driving factor. So how can we work on that one? And that's now expanding a bit more on how this actually works. The strategy behind laying out the data, or how HBase writes the data, is called log structured merge trees. Those log structured merge trees there's a paper out, you can read on that one. That's what Bigtable, when Google implemented Bigtable, used as well. The idea here is we get away from seeking on a disk, because seeks are the slowest operation on a disk. We actually trying to do everything as sequential as possible. So do like one seek and write a large chunk of data to really get the bandwidth throughput of the disk saturated. Otherwise, if you're just concerned with like if you have like a B tree typical database layout, you would have to jump left and right, and then you have to run these optimize commands on the database so it actually restructures them so that they're more closer to each other. But that's where the typical relational databases suffer at scale. And they try to get around this using this log structured merge tree. And the way that works is that whenever you do a mutation, it writes it into a, that's the other way around, it writes it into a write-ahead log. It's just a bin log like MySQL has, so it just writes it to this write-ahead log on disk, and once it's being it's confirmed that it's being landed, it writes it into an in-memory store, and then tells the client, done. It's secure, which means if the server crashes, we can replay that log, we have the data back, and everything is fine. But once while the server is running, it starts accumulating those in-memory data structures. So whenever you say you put a value into row 1, column 1, you put something in, it will actually put this into memory first. And if you do put, say, 5 minutes later, you put something into row 1, column 2, same row, it would put it next to each other. So by the time it has accumulated something in memory, enough data that it's worthwhile writing it out, there's a setting how much you want to accumulate, which is typically 128 megabyte. You want to sort of accumulate it in memory, and then it writes it out as a new file. These are called flushes. So the flush file is just an accumulated, sorted list of values. It's sorted by key, so that when it's written out, it's already nicely sequential, it's sorted, so you can actually go through and find data, during a scan in a sorted order by its main key. So that's basically a flush file. And we get to this in a minute, how to configure this and what this means. And I have this OR there. Typically, you want to have the flush happening when you reach the memory size, what you have configured. You want to flush decently sized files. If you get lots of small files, then HDFS, again being a shared resource, will have trouble because HDFS is not really great at lots of small files. It's good at typically fewer very large files. It's just the way that the name node works. It keeps every inode in memory, and if you have too many of those, you're putting stress on the name node and eventually running out of memory. So there's like there's another reason when files could be written out onto disk. That's when you are under pressure, and we get to this in a second. That's the important part. And once everything has been flushed out, you can discard the logs, the binary logs, those bin logs. You can throw them away with all the edits because there's nothing pending anymore. Whenever all of the memory has been written out that reflect a log file, then the log file can be discarded. But keep in mind, the log file is typically also so roughly the same size, 64 or 128 megabyte. So you have these these binary log files being created and data accumulated in memory. So it's not a one-to-one mapping. You could end up having a couple of these bin logs, and in memory, when you write this out, those flash files, because you will have multiple in-memory stores, it takes a while for those to be written out, and then all of the logs or the older log files to be discarded. So over time, you will see HBase accumulating a few of these log files, and the default setting is 32. There's a maximum number configured as 32. After 32 log files, it will actually tell you something is wrong here, because I should have like the oldest, the 32nd file is basically so old, there's like so many of them now, that I need to freeze something, I need to write something out from memory onto disk, and that's also causing these forced flushes. And again, you don't want to have those happen because they sort of interfere with the entire operation. And then finally, part of that log structured merge tree is that you have a regular operation that happens in the background that rewrites these files into fewer, larger files. They're called compactions.
Is there something to keep in mind, or a setting if you have, I mean, this is kind of getting a little bit maybe ahead, but a single version of, a cell,
Mm-hmm.
and if that's continually being updated, my understanding is that still takes place, that accumulates heap, and once that reaches this, what did you say, it was 128 megs before flush happens, even though you're keeping a single cell, is there any way to prevent that flush from happening?
What for?
So, well, at the end of the day, so I've heard that if you're only keeping a single value and you do a flush, it's going to realize that, hey, you may have numerous copies of this single cell, but I'm only going to keep the most recent, for example.
Most recent 3 typically, yeah.
So it'll do that flush, but at the end of the day, the size of that file that would be flushed would be minuscule.
Yes. So the question is, I have to repeat it, right? So can you somehow pin some of these in memory, right? So you keep them in memory, because otherwise, if you were to like keep updating the same data, it would just not really accumulate to enough to actually flush it out to disk, right? This is why these in-memory stores, they're shared across all of the rows, right? It's not just for one single value. If your client would only write always one single value, nothing else, then you're only holding this one single value in memory, and it would eventually be flushed out by time. There's also a time component that would flush it out. And that would actually result into something very small. But typically, that's not a use case for HBase, where you're only updating small things. Say if you do counters, HBase has this counter feature where you can actually update an existing column by increasing it atomically by a number, like typically by 1. If you do this basically constantly, this happens in memory, and then eventually one version of that counter will be flushed out to disk, and it keeps updating it in memory until it's basically another, I don't know, say another 10,000 higher, and it writes it out to disk. So, but you typically don't have like one counter, but you have many counters, and you have other fields that you update across the board. So that just happens automatically. Personally, I have never seen anyone having a problem with flush files never reaching the size. There is a problem with that, and I'll show you that in a minute, with these in-memory stores are actually per column family. So if you haven't talked about this, but if those that know HBase, HBase has this notion of a column family where you can group a couple of columns together in a sort of logical group. These in-memory stores are per column family. If there is a problem that when you write one column family with very large data or a lot of data, and one column family with really just a few data, currently, we're just working on this, I think some developers are actually picking this up. Currently, the flush is across all column families, which means if you have one large column family filling up and triggering the flush, you will have these other column families with just a little bit of data aggregated, writing out very small files. That can cause issues at the bottom there, the compactions. They're called compaction storms, because you're writing out lots of small files, which then have to get merged into larger files, which causes lots and lots of write amplification in the background, called compaction storms. And so there is some issues with that, but I've never seen it in a single instance. Mm-hmm.
As you keep collecting data through memory store, I take it you can also read the test at the same time.
Yes.
All the reads keep the memory store.
Yes.
So when the reads keep the memory store, does it also gets the block cache, or it bypasses it?
The question is, whatever is in memory currently, can you read it, and is it actually cached? It's cached automatically because it's in the cache, it's in a memory structure.
And then if you look at the statistics of block cache,
Yes.
will reads to the memory store affect it?
No. No, the block, so the question is, will the metrics reflect that, basically? Will it actually, I don't know, change the metrics for the block cache? The block cache is completely separate. So block cache, if you were to go out to disk and actually try to read a block, anything that you do in memory is not being accounted for. It's just happening. No, it's not duplicated. We have these settings where you can actually say, when you flush something out, when you do that flushing, actually put it straight into cache, so that the next time around that you don't have to go again, load it again, because you just have written it out. Keep it in memory. There's a cache on flush option that you can enable if your use case warrants that. If you need that data constantly, you can enable that.
Right.
Yeah. Right. So this is so the log structure merge tree is the concept behind that. This just predates Google's building Bigtable. That's like it was an attempt to build a system that doesn't have that drawback of the typical B tree or B plus tree based storage format. They use this one to say we're accumulating stuff, writing it out in larger files sequentially, and when we ever look at this, we're reading it sequentially as well, and that makes it more efficient. The write performance, we basically on the other side, for the performance side, there are many factors on how to actually do this right. Now, I have another talk where I talk more about like schema design, which sort of hits that on the head. But the point is, important is that you have to watch out for key distribution. If you write something to HBase and you do time series again, and you write something like a key is sequentially monotonically increasing and is sorted monotonically increasing, then you're always hitting the same server. The way it's done in HBase is that a certain server serves a range of keys. So if you have a range of keys and you keep writing to that range, you're only hitting one server. So that's called hotspotting on a single server, so region hotspotting or server hotspotting. So you make sure that when you want to have best performance of your cluster, that you have some distribution in your key. Or if you don't want to do that because at write time you want to have sorted, timestamp keys, then you have to use bulk loading to get this in there, because otherwise you can't avoid that problem. You have to find a way in between. Either prefix your key with an ID, so you bucket them into different groups, but you need to find out how you actually write into the server. So when you have a load on HBase, go to the UI or go to the metrics and have a look per server what the insert rate is. If you're only seeing one burning and the rest is idle, that typically means the keys are linear or like sequential, and it hurts. I mentioned this, the handlers. Watch out for the handlers. Don't pile up too early. This means just keep an eye on the handler count. Again, there are metrics for that. If you go to Ganglia, type in handler and look at all of the metrics that have handler in it. It will show you where it sits, and then compare this with the settings. If you get to the maximum of the handlers, then raise them slightly to see if that actually helps you alleviating the situation or the pressure.
Are those metrics exposed in Cloudera Manager as well?
The question is if the metrics are exposed in Cloudera Manager, and yes, they are, all of them. Yeah. Like the latest version 4.5 onwards, and then 5 that came out yesterday, or the beta came out yesterday, there's much more even. You have like a language where you can actually get any sort of metric pulled in and create your own dashboards with different ones. So you don't need Ganglia anymore. I didn't want to mention this because yeah, it looks like a product set here. The crucial part for write performance that I see at the moment, there is still no solution for that, is the write-ahead log. You mentioned earlier you have this write-ahead log, so whenever you write first to the write-ahead log and then put it into the mem stores. Now the problem is you do this for every single operation across all clients and a single write-ahead log for a client. So you're ending up with a single writer problem that you get to the maximum speed of what HDFS can give you to write files, and that drives the performance of a single server. And that's a crap value at the moment, I have to say this. Because so natively, HDFS can go up to, say, 50, 60 megabytes per second writing. But if you go through all of the other hops in HBase, that value is typically somewhere around a very low mark. I'll get to this in a second. I have this in my math. But that is currently the number one bottleneck, and we do not have an answer for that. I'll get to this in a minute, what you can do about that. Then compactions, I mentioned this. This is just a background operation that rewrites the files and on a regular basis. You can tune those. Look at those. That will help you. The default is okay, but I had this at a customer. We were like load testing HBase. And over the course of 3-4 days, HBase was like the latency in HBase would get slower and slower and slower and slower. So it was like constantly, if you zoomed out, you could see how this basically was a linear line, just saying, okay, slower, slower, slower. We were like here, over there, somewhere when we started. Now we're over here up today. And so it seemed like there's never going to like sort of even out and reach sort of like an even point. The problem was that the compactions were badly tuned. So in the background, these compaction storms caused this like a write amplification. There's an asynchronous write operation that just sucks away your HDFS resources by rewriting files constantly in the background. And if you don't pay attention to that one, your overall performance just goes slower and slower and worse, basically, over time. But you can tune that by sort of topping off when HBase starts like looking at files as a couple of settings. And then if you do that, you can tell it, well, it's fine. Do not just aggressively compact. Take it a step back and take it easier, because typically you do not have to compact that aggressively. For certain workloads, for most workloads, you can actually leave a few files there. You do not have only have 2 or 3 files. You can have 5, 6, 8 files. So there's a ratio setting, compaction ratio you can look into. You can tune this down. It's 1.2 at the moment. Maybe set it to 1 just to try it out. And there's a few more, 1 or 2 more in that. If you look in the settings for compactions that you can try out and see what happens. But that's another one that cuts into your performance. I mentioned the write-ahead log. Let's go back to the write-ahead log. So it's only 1 per server. They're shared across all stores, all column families, all memory stores, all stores that are happening in memory. They are shared. and they have the synchronized file append call, and that somehow bottlenecks the entire operation. I'm saying there's no solution for that. Work is being done. We have added write-ahead log compression, which helps reducing the I/O. So we're just reducing how many bytes we write. Therefore, we get a bit more performance. Compression helps. Enable that. Make sure it's enabled. And the other thing is we have some work being done. Or if you have been to the conference yesterday, there were mentioning of multiple vals. That's not what I want. The multiple vals that I want is multiple vals that write in parallel. There were talk yesterday, like the developers yesterday talked about, my colleagues, they talked about multiple vals. If one goes slow, you fail over to another one. That's what was in the original Bigtable paper, that you have, if you have latencies on one, you fail over to the other, and then you can fail back. So you're writing to two just to make sure that you do not hit a slow disk with one constantly, so you can fail over to another set of machines and try again and be faster. But this is not what I want. What I want is really just a multiple one to have, not having a single writer, but have multiple ones. I actually resorted, and that's like a really dirty one, I resorted to starting multiple region servers on a single physical node, just to get around this, and then we hit the target. That's like your last resort. I'm hoping this is resolved soon. Write-ahead log, the default setting, I said is flushes as 164, 128 megabyte. You have to check your configuration. It's typically 95% of the default block size, which is by normal modern distributions. They have 128 megabyte, so 95, so just under 128 megabyte. It actually starts flushing. It's set to 32. I mentioned this, but you want to make sure that you do not get to that limit. So keep the number somehow low to keep recovery time in check. So there's this upper built-in limit of 32. It's actually a hidden configuration parameter. It's not in the default setting. That is something you have to, you can find if you look at on the web, you can find it. But that's something that is set to 32 and can cause issues, and I'll show you in a second why. Then you have some options to get around this limitation. You can either increase the log size, make them a little bit larger, so you don't have to get up to 32, make them double the size, set them to like 256 megabytes, so they get slightly larger. Takes a little bit more time to sort of split them, but you're getting away from the 32. Or you can increase the number of logs. I've done this too, like it has changed this hidden setting to from 32 to like, I don't know, a higher value, 50, or I had a customer had it 128. Otherwise we couldn't keep up with the insert rate. That's the way it is. And you compute that number based really on the fill distribution of flush frequency, and I'll get to that in a minute and I'll show you how this works. That's the takeaway for today. Continued on the write-ahead log, the writes are synchronized across all of the stores, and that means if you have a very large cell being written, if you have, I had an example as a customer, they were writing, there was a message store for like a telecommunication system. They were writing MMSs, SMSs, IMs, and whatever into HBase. And MMS, which is was in this test case 2 megabyte in size, and an SMS and an IM, like instant messaging, they're typically very small, like a Twitter message, like a couple of bytes. The problem is what we saw is that the insert rate of the SMS, which was much higher, like 1,000 times higher than the MMS in terms of ratio, but whenever an MMS came in between, it sort of blocked up all of the writers for the SMS because they had to wait for this large little thing there, like this blob going through the channel, through the write-ahead log. And sort of when you looked at the RPC, they all went green. If you use visual, what's it called? Not J console, the new one, Visual J, or was it Visual VM? Yeah. You could see the threads basically, all green, and all of a sudden when this SMS came through, they all went red. They all blocked. And then all of them, they would green again, and then blocked again, and green again. This really just sort of hurts your overall performance. Again, I would wish to have multiple write-ahead logs, so the other ones would go to other write-ahead logs. That would fix this problem, but it's not there yet. So that's when your handlers go binary. They all block or they all work. You will see this in the thread overview in Visual VM. You can switch this off. You can actually switch the write-ahead log off, but if you do that, there's no chance that you can recover after a crash, so be careful with that one. I had this at a customer where I only turned it on for the main record, and all derived records, I turned it off The reason I did this is that when a crash happened and a replay kicks in of the main records, there's a hook that you can use to sort of listen into when this replay happens, and then I created the derived records at that point, so that during most of the time I would not have to write into the write-ahead log for those derived records, but for the during replay I had to somehow get them back, right? Like index, for example, secondary indexing is one of those. You have a big main record and a small lookup record. I didn't put I switched off write-ahead log for those tables just to get to the speed that I needed for the main ones, and during replay I would recreate the secondary indexing. Yeah?
Is there a way to conditionally bypass it as the data is coming in? For example, the data, we have a use case where we need to capture the fact of something, but we may with some updates for this fact.
Yeah, the question is if we can do this conditionally. It's per write, so you can, for every write you can decide if you have it or not. So every operation, every mutation, like the delete or the put, has a flag that you can set for this operation, turn it off or turn it on. So you can do this whatever you want. But from the client side, you need to know that there's no rule on the server side. You have to, from the client, say, yeah, these are fine. Just if I lose one, turn it off for those. That's fine. Yeah.
That's a parameter on the put.
Yes. Yeah, right to well. No, has a right to. I said right to well. Getting back to the flushes, right? I mentioned the flushes is when things are accumulated in memory and then it flushes out to disk. So every mutation, every put and delete, increment, they cause a check. So whenever you do something, there is a check saying, okay, have I enough in memory now? So they will put it into the write-ahead log, will put it into memory, and if I have enough, then it was being written out to disk. So that's basically what happens. And then once it has been written out to disk, it asynchronously schedules one of those compactions. It says, yeah, I've just written out something. See if you can actually write them together right now, because eventually you have to do it anyway. So it triggers this compaction to sort of quickly compact the last few flushed files for you. It's like a minor compaction, it's called. And eventually, when the compaction comes back, it would tell the server as well, I have enough files now, the region is full, there's a maximum size, a total size of files I want to have in, a total file size I want to have in a region, which is set to, say, 1 gigabyte, but typically we see them at 5 or 10 gigabytes in practice. Once I reach enough data in that one directory with all of these files, and these files together, the sum of them surpasses that limit, it will say now we have to split, and it will split it into 2 regions, do the distribution, and that's how HBase scales out. But that happens during the flushes. Now, I already mentioned this, couldn't recall, I actually have a slide on that one. So the compaction storms is exactly this problem that if you have too many of those logs, if you're the write-ahead logs, if you get that to at 32, and there's a couple of other reasons, if memory basically is just exceeded, then there's pressure on the system, and then the system will say, write them out now. You have to. I'm running out of either main memory, or I have too many files accumulated. Start flushing stuff out to disk, and that causes that instead of getting these nice large files which you can move around and they make sense, you're getting lots of small files. So whenever you go and grab your logs and search for flush, typically what I do is I do a grab, filter it through tail the log files on the server, grab it basically by flush and have a look at what I see and messages, and it will print out the sizes of the flushes. There's also a metric for the average flush size which you can look at, but I typically just go straight to the logs. It will tell me that I'm flushing, say, 1 kilobyte here, 10 kilobytes there. It's like, that's way too slow because I want to do 128 megabytes, not kilobyte size. And that tells me something is wrong, something is misconfigured. Now, we get to the math why in a second. And so what happens is that in the background, the compactions try to keep up with the files being created. And the way the default is configured, the problem is it writes this 1 kilobyte into a 1 kilobyte, so it ends up being 2 kilobytes, and it's another kilobyte, another kilobyte, another kilobyte. And in the end, you have, like, say, a 300 meg file, and you're starting to rewrite that 300 meg file to merge in 1 kilobyte per flush. And that background is rewriting that 300 takes some time, then all of a sudden you're at 600, 700 megabyte. And that causes this background issue, because that background write amplification, because you're merging these tiny little files in this huge file. You shouldn't do that. So this is where you have to tune then your compaction selection to say stop somewhere when the file reaches 256 megs. Ignore them. Don't start compacting them. Leave them alone.
There's something built in there that.
No, it's only like you can tune it. There's a top limit. As a HBase HBase region server compaction size max dot size. You can actually top this off. You can say stop considering these files for compactions once they reach a certain size.
Actually, that's not exactly what I meant. There's something that did that you flush two little chunks of data rather than flushing bigger chunks. Like for example, for the last 5 minutes, I flushed 10 kilobytes file.
Yeah.
And wait for 10 minutes to flush it.
What does all this? So just to repeat the question, what should the system do for you?
For the last minute, instead of waiting until the file grows until I did 1,000 flushes. Kilobytes.
It would compact those anyways first, right? So
So those are different flushes, right?
yes.
Different places.
No, not different places. Flushes happen in the same directory. They all go in the same directory. They're all sitting next to each other. It's like you can see those files basically all in one directory on HDFS. And they would look at these and say, there's like that many, and which one? It only grabs 10 used anyway and rewrites those. There's a couple of settings. If you look into those, you can see those.
So can you control the splitting and compaction? Can it be controlled manually or?
Can you control the splitting and in other ways? Yes, you have the configuration you can use. I can sort of configure that. Some you can configure per column family, like the split size, like the region size. You can do this per column family. And some you actually have these coprocessors that I mentioned. You have a hook on the server side that you can actually hook into to somehow do something on the fly. But that's like that's the hardcore programming side of things. I would start with the configuration and what you do in the schema when you define the column families. Sorry, I have to hurry up. I'm just running out of time. So compaction storms, that's the reason. So the dependencies are really flushes happen across all of the stores currently. So whenever something is triggered, you trigger one, all of them have been written out. And the flush size, as I mentioned this, you're basically compacting. The flush size is the combination of all of the column families. So if you have 3 column families and you accumulate and you have the flush size set to 64 megabyte and the first one reaches 55, the other 5 and 4 together 64, it would start flushing, right? So the flush size is not even when one reaches that size, it's the combination, the sum of all of the in-memory stores across all of the column families. Keep this in mind when you set the flush size and you have multiple column families. You need to adjust maybe the flush size slightly higher. Set it higher so that across all of them, they have a better chance to reach a nice file size. It's a bit convoluted or a bit strange, but that's the way it goes. Now we get to the last part, like some numbers. Typically, as I said, if you assume 35 to 50 megabytes per second on the HDFS side, that's what you should be able to do on the HBase side. You should be able, with 1 kilobyte row sizes or cell sizes that you're writing, you should be able to do 35 to 50,000 per second on a server. That's not happening. The one that I have in black is more likely, but the other ones I just extrapolated. I just used the same. I just straight math, saying if I have a look at how much I can do in terms of size, that's what I should be able to do. That's not going to work. So really, what I'm seeing is this. I'm really just seeing 50 megabytes per second or less on the HBase side. We need to work on this. Like HBase, the developers are aware of that. We need to be better. But currently, if you were to build a system and you want to do the math, how many servers do I need, how much do I write, take about that number and then look at, I just extrapolated this in a table. If you want to insert typically, say, 1 kilobyte records into HBase, you can do about 6,000 per server, not more. And then goes down. If you do the half a meg, you can only do 10. Remember my example with this MMS with 2 megabyte? This goes even further down. You can only do like 3 or so per second.
Including the wall or not?
Yeah, that's the wall. That's because of the wall. Because of the wall, that's the time. If you switch off the wall, this goes way up. I'd say by factor 5 to 10. Yeah. So it's really just that single writer problem on the wall, bringing down the time there, because the single writer only gives you that time. In HDFS, it's a parallel file system. You can have like 1,000 writers, 1,000 threads writing to HBase, HDFS to different files on different servers. Because if you have enough disks, they all can actually do 100 megs per second on each of these disks. So you have enough spindles. But because of that single rider, you're ending up going through this one bottleneck and really hurting on that end. That's exactly the reason. So let's, I'm wrapping this up now with a few notes. To compute the memstore size, like this is the one that actually decides how much you actually accumulate before you flush out. You have to actually do the math of seeing how many regions do you have, and then times this the flush size. And I have a sheet on this one in a second. You have to compute the number of logs based on that fill and flush rate. So depending on how much you take in terms of writes, just do the math, how many kilobytes you take into writes, and then see how many of these you accumulate in a certain amount of time. Again, I have a calculation on this in the end. That sort of drives how much you can actually do per server. So ultimately, this capacity of HBase of a region server is driven by the heap size, the region count and the size of the account, the size of the regions, and the key distribution in general. Otherwise, you're hitting a single server. That's not good. So the cheat sheet I have, like 2 of them, and show you have enough, or large enough, write-ahead logs so you don't flush early. Make sure you do not oversubscribe the available memstore size, because then you flush early again. Ensure that the flush size is large enough and but not too large. You don't want to make sure you don't want to keep too much in memory, because then you keep too many write-ahead logs around. So you can go up to say 128, so it's 256 megabyte. But if you go like way beyond that, it's not practical anymore. And check if you should use or not use the write-ahead log, only if you can't avoid anything else, right? That's the last resort. Enable compression. Compression means less I/O, therefore faster. Definitely always enable compression unless you have like JPEGs or something that's already compressed. Always use compression. Tweak the compaction so that you have that you keep the background I/O in check. Like tweak that ratio, the upper limit, and that's important under load. Consider putting uneven column families in separate tables. Then you have to avoid somehow the combined flushes of large and small column families. You might just have to break them apart. Again, that's when it really gets nasty because you're hurting a lot. Typically, you don't have to do this, but if you get into that hurt locker, then that's the way to get out, hopefully. And check the metrics, like search for block hash, search for memstore, and queues. Queue is another sort of, I type in queue and see with the metrics that show me, is it backed up or is it actually up to what it should be? All right, last slide. Here's the math. Assume you have 10 gigs of heap for the Java process. 40% I said by default is for the memstore, 20% for the writes. So 40% is 4 gigs. For the right side, you want to have 128 megabyte flush size, so divide this, 4 gig that you can actually keep there, divided by 128, you can only have 32 regions maximum. And 32 is also interestingly, if you do the math, I said the flushes, the write-ahead logs get rotated at 95% of the block size, which is, if you do the math, meaning that by the time you fill up 4 gigs of memstore, you're having about 33 uncommitted, partially uncommitted write-ahead logs lying around before all of the memories get written out, and then they can all be thrown away. That means the 32 setting, that is the default, is sort of already at that brink. Typically, because of changing workloads, you don't hit this, but that's where this comes from, right? So you have to be careful. Is that number high enough, or should I slightly increase the write-ahead log to actually fill those 4 gigs of memory? And then if you have a region size of 20 gig times 32, you can really only address 640 gigabytes of data per server. So if you build a HBase cluster, my last advice for you is do not buy many highly like storage-heavy server. Buy easy, simple servers with only, say, 6 disks of, I don't know, half a tera or a tera each, and have more of those. Like parallelize the whole thing. So this is different from the Hadoop workloads. So overloading Hadoop and HBase, you can do that. But if you build a pure HBase cluster, design it slightly differently. Go for more iron, more bare metal, which is slightly lesser spec than you would do typically for a Hadoop solution. Final questions. Are we already questions between any? Yeah, that's.
Is there a way to plug in your caching strategy for example, the block? The reason I ask for block caching is because it gets the same of this.
Mm-hmm.
But if I can predict my reads, they go from here to here to here, and accumulate it in 64K.
Okay, so the question is ways to sort of like plug into the cache strategy and like what it gets from where. The default is what I mentioned, but we have hooks into that system nowadays. There's actually companies that produce SSDs and memory and flash disks that I think it was a Fusion IO, one of those. They actually contributed a patch back to HBase that you can use that you use one of their SSDs as the target for the cache. So you can now all of a sudden, instead of having just the memory cache, whatever the 4 gigs, or this was only 2 gigs in this example, for the block cache, you could actually then put this onto like a 256 or 1 terabyte SSD to do the caching there. There's a whole different idea of caching, and then this helps a lot, obviously, to sort of speed up the read side and keep the working set in memory. So that you can plug in, but not on the fine-grained level that you were saying, that you accumulate, that you have the right thing in memory. That you would have to do by designing your keys properly so that data that you need together is sorted together. Keep in mind, everything is sorted. So if you want to have data that you typically read together.
But then you can have hotspots together.
Yes, exactly. Yeah, exactly. You can have hotspots. So, but typically what you do is you break out the hotspots into multiple, say if you have 10 servers, you would bucket the key into 10, about 10 partitions, and then you would have to read from 10 to reconstitute the range, but you would distribute this across all of the servers. So there's ways to get around this, or as I said, you can use bulk loading to load it from the side, and then basically you don't have this problem with hotspotting at all because you don't use the right pipeline.
Is there anything that should be kept in mind for HBase 96?
Is there anything to keep in mind from the HBase 96? There's
Talking about kind of deprecating key value and moving on.
Yeah, that's like 96. So the question is about key value and whatever. If you were to use that lower level concepts, if you were to talk to actually the raw key values, that was going to change. They're deprecated now, and we're changing over to the cell concept. Because we need to abstract this. At the moment, the key value is the raw byte array that you can actually manipulate and look into. That has to be abstracted. In the past, it was great to have the raw access, so you can do zero copy operations on it. But the cell one is needed because we want to add cell level security tags that we can actually use, similar to Accumulo, that we can do proper security and you can tag things. We need to have a layer in between. So it's the only real sort of change that that would reflect if you were to go that level down. But otherwise, you can just fairly straightforward change over to 96 without much ado. But obviously no one has done it in production. These days a lot of people use distributions, and they use therefore stable releases, which means use CDH, for example, which has 94 in it, and others have also like 94, typically HBase in it. CDH5 has 96 in it, so you can start testing it out, just see if it's compatible or not. Most of the API is the same. We dropped the row logs because they were a bad idea anyways. They don't work distributed. This is the whole idea about not having anything locked across the distributed system. So there's a few things that we dropped or had changed or had to deprecate, but the majority is the same. I'm here anyways for like I have another talk after lunch, and then if you have questions, please feel free to ask. Thank you.